The past is gone. Everyone knows this. It happened. It's over. It's behind us. We remember it, sure, but it doesn't exist anymore. Right? Wrong. Completely, fundamentally wrong. And Richard Feynman, one of the greatest physicists who ever lived, can explain exactly why. The past isn't gone. It never left. It's still here, right now, woven into the fabric of everything you see and touch. And once you understand why, you'll never think about time the same way again. Let me show you what I mean. Right now, you're sitting somewhere, reading this, existing in what you call the present moment. You think of now as a single point in time, a razor's edge between past and future. The past is behind you. Done. Finished. The future hasn't happened yet. And you're stuck in this tiny sliver called now. But here's the thing Feynman understood. That picture is wrong. Completely wrong. Time doesn't work that way. The present moment isn't a point, the past isn't gone, and the future isn't waiting to happen. It's all more connected, more intertwined, more simultaneous than you've ever imagined. Now, Feynman had this incredible gift for taking the most mind-bending ideas in physics and making them feel obvious, almost simple. And when it came to time, he saw something that most people miss. He saw that when we talk about the past being gone, we're making an assumption, a big assumption. We're assuming that time flows, that it moves forward like a river, carrying us from past to future. That moments happen and then disappear, replaced by new moments. We think of time like pages in a book, where you're always on the current page, and the previous pages, well, they're behind you. You can remember them, but they don't exist in the same way the current page exists. But what if that's not how it works? Here's what Feynman would tell you. In physics, in the actual mathematical description of reality, time doesn't flow. It just is, all of it. Past, present, future, they're all equally real, equally existing. They're all part of the structure of the universe, like different locations in space. Think about it this way. You don't think Los Angeles stops existing when you're in New York. You don't think New York disappears when you travel to Los Angeles. They're both real places. They both exist simultaneously. You just can't be in both at once. Time, according to physics, works the same way. Yesterday is a place in time. Tomorrow is a place in time. They're both real. They both exist. You just can't be in both at once. You're located at today, but that doesn't make yesterday any less real than Los Angeles is when you're in New York. Now, I know what you're thinking. That sounds crazy. You can go to Los Angeles. You can get on a plane and fly there. But you can't go to yesterday. You can't travel to the past. So how can they be the same? And that's a fair question. But here's the thing. The reason you can't travel to yesterday has nothing to do with whether yesterday exists. It has to do with the structure of space-time and the laws of physics. There are restrictions on how we can move through time, just like there are restrictions on how we can move through space. You can't travel faster than light through space. That's a law of physics. But that doesn't mean the places beyond your light cone don't exist. Similarly, you can't move backward through time under normal circumstances. But that doesn't mean the past doesn't exist. Feynman understood this at a deep level. He worked with something called the path integral formulation of quantum mechanics. And in that formulation, particles don't just take one path through space-time. They take all possible paths, every path, simultaneously. A particle going from point A to point B doesn't just travel in a straight line. It explores every possible route, including ones that loop backward in time, ones that zigzag wildly, ones that take detours through every corner of the universe. And all of those paths contribute to the final result. All of them are real, in a sense. Now, the paths that go backward in time, the ones that violate our normal sense of causality, they mostly cancel out when you add them all up. They're there, but they interfere with each other and don't contribute much to what we observe. But they're not forbidden. They're part of the mathematics. They're part of how the universe actually works at the quantum level. And this reveals something profound. The distinction between past and future, the arrow of time that feels so obvious to us, it's not fundamental. It's not built into the basic laws of physics. The equations work the same whether time runs forward or backward. If you filmed the interactions of particles and played the film in reverse, you couldn't tell the difference. The laws don't care. So where does our sense of time's arrow come from? Why does the past feel different from the future? Why do we remember yesterday but not tomorrow? Feynman knew the answer. It comes from entropy, from the second law of thermodynamics, from the fact that disorder increases over time, but that's a statistical law, not a fundamental one. It's about probabilities and large numbers of particles, not about the deep structure of time itself. Let me explain what that means. Imagine you have a box of gas molecules. At the start, all the molecules are in one corner of the box. That's a low entropy state, a high degree of order. Now you let the molecules spread out. They fill the entire box. That's a high entropy state, more disorder. And here's the key. This process is much more likely to happen than the reverse. It's incredibly unlikely that all the molecules would spontaneously gather back in one corner. Not impossible, just fantastically improbable. So when we watch this system, we see entropy increasing. We see order turning into disorder. And we say time is moving forward. But notice something. The molecules themselves don't know about time's arrow. Each collision, each interaction between molecules could just as easily run backward. The laws governing those collisions are time-symmetric. The arrow of time emerges from statistics, from the fact that there are vastly more disordered states than ordered states, so systems naturally evolve toward disorder. That's it. That's where our sense of past and future comes from. Not from time itself, but from entropy. Now, here's where it gets interesting. Because of this, because the arrow of time is statistical and not fundamental, there's a sense in which all moments in time are equally real. The past hasn't gone anywhere. It's still a part of space-time, still a valid location in the four-dimensional structure of the universe. When physicists write down the equations describing the universe, they include all of time, past, present, future. It's all there in the mathematics. It's all part of the solution. The universe, from this view, is a four-dimensional object. 3 dimensions of space, 1 dimension of time. And just like every point in space is part of the object, every moment in time is part of the object. The Big Bang is part of it. The moment you were born is part of it. This moment right now is part of it. The heat death of the universe billions of years from now is part of it. All of it exists. All of it is real. We just experience it sequentially because of how our consciousness works, because of how memory and causality function in a universe with increasing entropy. Feynman had this way of making you see that our everyday intuitions about time are parochial, limited. We think time flows because we experience it flowing. We think the past is gone because we can't go back to it. But those are facts about us, about our perspective, about the limitations of our consciousness and memory. They're not facts about time itself. It's like the bug on the ball from that other example. The bug thinks its universe is two-dimensional because it can't perceive the third dimension. We think time flows because we can't perceive all of time at once, but the flow is an illusion created by our particular way of experiencing reality. Now, let me show you something that'll really bend your mind. You know how we think of ourselves as moving through time. We imagine we're traveling forward, 1 second per second, from past to future. But there's another way to think about it. What if you're not moving through time at all? What if you exist at all moments simultaneously, and consciousness is just the experience of different time slices of that four-dimensional object that is you? Let me explain. Imagine your entire life as a long, worm-like object stretching through space-time. One end is your birth, the other end is your death. And in between, every moment you've ever experienced, every moment you will ever experience, they're all part of this object. This four-dimensional worm is the real you, the complete you. Now, at each moment, you're only conscious of a thin, three-dimensional slice of this worm. You experience one moment at a time. But that's just your perspective. From outside time, from a God's eye view, all of you exists at once. You at age 5, you right now, you at age 90, all equally real, all equally part of the structure. This is called the block universe view, and it's a natural consequence of Einstein's special relativity, which Feynman knew intimately. In special relativity, there's no universal now. Different observers moving at different speeds will disagree about which events are simultaneous. What I call now, you might call the past or the future, if we're moving relative to each other. And if there's no universal now, if simultaneity is relative, then the present moment isn't special. It's just a particular slice through space-time that you happen to be experiencing. And that means the past and future are just as real as the present. They're other slices through the same space-time. Okay, now watch this, because this is where Feynman's genius really shines. He didn't just accept this abstract picture. He showed how it actually works in practice, how it explains real phenomena. Take antiparticles, for example. An antiparticle is like a normal particle, but with opposite charge. The antiparticle of an electron is a positron. Same mass, opposite charge. Now, Feynman had this incredible insight. He realized that you can think of an antiparticle as a regular particle moving backward in time. I'm not kidding. This is actual physics, not science fiction. When a positron moves forward through time, it looks exactly like an electron moving backward through time. The mathematics is identical. And Feynman used this idea to develop his famous Feynman diagrams, which are pictures showing how particles interact. In these diagrams, time is usually shown going upward. A particle moving up is going forward in time. A particle moving down is going backward in time, which we interpret as an antiparticle moving forward in time. Now, here's the beautiful part. This isn't just a mathematical trick. It's revealing something deep about the nature of time and particles. It's showing that the distinction between past and future, between particle and antiparticle, is more subtle than we thought. It's showing that time-reversed processes are just as valid as time-forward processes. And it's showing that the past is still there, still part of the structure, still contributing to the present. Because when you calculate what happens in a particle interaction using Feynman's methods, you're summing over all possible paths, including the ones that loop backward in time. Those backward in time paths correspond to antiparticles, and they're essential to getting the right answer. Without them, the calculations don't work. The past, in this sense, is actively participating in the present. Let me give you another example. Light. You see light from the sun, right? That light was emitted 8 minutes ago because it takes 8 minutes for light to travel from the sun to Earth. So when you look at the sun, you're seeing the past. You're seeing what the sun looked like 8 minutes ago, not what it looks like now. And when you look at distant stars, you're seeing even further into the past. Some stars are thousands of light years away. The light you're seeing was emitted thousands of years ago. That star might not even exist anymore, but its light is still reaching you. Now, here's the thing. That light, that information from the past, it's still real. It's still here. It's still part of the universe. The past is encoded in the light traveling through space. It's not gone. It's in transit. And not just light. Gravitational waves work the same way. When two black holes collided billions of years ago, they sent ripples through space-time. Those ripples traveled across the universe, and we detected them in 2015 with LIGO. That event from the distant past reached us in the present. The past, in the form of those waves, crossed billions of years to arrive here and now. So the past isn't gone. It's embedded in the universe. It's in the light reaching us from distant stars. It's in the cosmic microwave background radiation, the afterglow of the Big Bang, which we can still detect today. It's in the fossils in the ground, in the rings of trees, in the layers of ice in glaciers. Every part of the universe carries information about its past. The past is written into the present. It's not separate, it's not disconnected, it's part of the continuous structure of space-time. Now, Feynman would push this even further. He'd say that when you interact with something, when you touch a table or see a tree, you're not just interacting with that object in the present, you're interacting with its entire history. The atoms in that table were forged in stars billions of years ago. Those stars exploded in supernovas, scattering the atoms across space. Those atoms eventually came together to form the Earth, and then the wood, and then the table. Every atom carries that history, and when you touch the table, you're touching all of that. The past is physically present in the structure of matter. Here's another way Feynman thought about it. He was obsessed with the idea that the universe might be deterministic, that the present state of the universe completely determines both the future and the past. If you knew the position and velocity of every particle in the universe right now, you could, in principle, calculate what the universe looked like at any point in the past and what it will look like at any point in the future. The information is all there. It's encoded in the present. Quantum mechanics complicates this, adds uncertainty, but the basic idea holds. The past isn't erased. It's compressed, encoded, preserved in the structure of the present. Let me tell you something Feynman said that really captures this. He once remarked that from the perspective of a photon, a particle of light, no time passes at all. A photon travels at the speed of light, and at the speed of light, time dilation becomes infinite. From the photon's perspective, it's emitted and absorbed in the same instant. It doesn't experience duration. For the photon, the entire journey from a distant star to your eye happens in zero time. Think about what that means. For the photon, there is no past and future. There's only one eternal moment. And in that moment, everything that we perceive as separated in time is simultaneous. The star emitting the light traveling through space, you seeing the light, all the same instant from the photon's point of view. Now, obviously, we're not photons. We experience time. We have memory, causality, a clear sense of before and after. But Feynman's point is that our experience isn't the only valid perspective. The laws of physics describe a universe where time is more flexible, more relative, more interconnected than our intuition suggests. And when you take those laws seriously, when you follow them to their logical conclusions, you find that the past doesn't disappear. It remains as a valid part of space-time, as real as the present, just located at different coordinates in the four-dimensional structure of the universe. Here's the thing, though, and Feynman would be the first to admit this. This doesn't mean you can change the past. You can't go back and undo what happened. The past is fixed, frozen, unchangeable. Not because it's gone, but because it's already part of the structure. It's like asking if you can change New York while you're in Los Angeles. You can't. New York is what it is, whether you're there or not. Similarly, yesterday is what it is, whether you're there or not. The block universe view says all moments are equally real, but it also says they're all fixed. The past exists, but you can't alter it. Time travel, in the sense of going back and changing things, creates paradoxes that physics seems to forbid. But, and this is crucial, the past still affects the present. It's still causally connected to now. Everything that happened before led to this moment. The past is the foundation on which the present is built. And in that sense, it's not gone at all. It's more present than ever. Every memory you have, every scar on your body, every skill you've learned, every person you've met, all of that is the past persisting in the present. You are, in a very real sense, a living record of your past. The atoms in your body are remnants of dead stars. The patterns in your brain are shaped by experiences you had years ago. The past lives in you. It's not behind you, it's inside you. Now, let me address something that might be bothering you. If the past still exists, why can't we access it? Why can't we go back? Why does it feel gone even though physics says it's still there? And the answer comes back to entropy, to the arrow of time, to the statistical nature of why we experience time the way we do. Imagine a movie playing forward. You see events unfolding, things happening in order. Now play the movie backward. You see the same events, but in reverse. The physics of individual particles doesn't care which direction is which. But when you have many particles, when you have macroscopic objects like people and planets, entropy gives you a direction. Things break. They don't unbreak. Eggs shatter. They don't spontaneously reassemble. And our consciousness, our memory, is tied to this entropy increase. We remember the past because low entropy states evolve into high entropy states, and that evolution creates records, creates memory traces, creates the feeling of time passing. But here's the kicker. From the block universe perspective, memory isn't about the past being gone and then recovered. Memory is about different time slices of you having access to information from other time slices. Your brain right now contains patterns that were created by your brain 5 years ago. That's a physical connection across time. It's not mysterious. It's just information being preserved in a structure that persists through time. And that persistence is possible because the past and present are part of the same continuous space-time. If the past were truly gone, if it didn't exist, there would be nothing to remember. The fact that you can remember the past is evidence that it's still there, still part of the structure. Now, Feynman loved thought experiments. He loved taking ideas to their extremes to see what they revealed. So let's do one. Imagine the universe is like a film reel. Every frame is a moment in time. When you watch the film, you see one frame after another, and you perceive motion, change, a story unfolding. But the film reel itself, the physical object, contains all the frames simultaneously. They all exist at once on the reel. You watching the film corresponds to you experiencing time, but the film doesn't care about your experience. All the frames are equally part of the film. The universe, according to this view, is like that film reel. All moments exist simultaneously in the structure. We experience them sequentially, frame by frame, but they're all there. The past frames aren't gone. They're still on the reel. We just can't rewind and watch them again because our consciousness only moves forward through the frames. Okay, here's another mind-bending thing Feynman understood. Quantum mechanics, the theory governing the behavior of particles at the smallest scales, has this weird feature. Particles don't have definite properties until they're measured. Before measurement, an electron doesn't have a definite position or velocity. It exists in a superposition, a combination of all possible states. And when you measure it, the superposition collapses, and you get one definite outcome. Now, here's the strange part. The act of measuring affects not just the present, but also the past. There's an experiment called the delayed choice experiment. You send a photon through a setup where it can take 2 different paths. But you don't decide how to measure it until after the photon has already committed to a path. And what you find is that your choice of measurement in the present seems to determine which path the photon took in the past. It's as if the present reaches back and affects the past. Now, this doesn't mean you can send messages to the past or change history. The mathematics prevents that. But it does mean that the relationship between past and present is more entangled than we thought. The past isn't a fixed, independent thing that's completely separate from the present. The present helps determine what the past was. And this makes sense in the block universe view. If all of time is part of one structure, then correlations can exist across time, not just across space. The past and present are connected, not just causally, but in deeper ways revealed by quantum mechanics. Feynman worked extensively on quantum electrodynamics, the theory of how light and matter interact, and in QED, the fundamental entities are events in spacetime. An electron here emits a photon. The photon travels. Another electron there absorbs the photon. Each of these events is a point in spacetime, and the theory calculates the probability of different sequences of events. But notice what's happening. The theory treats time and space on equal footing. Events are located in space-time, not separately in space and in time. The past events, the present events, the future events, they're all part of the same calculation. They all contribute. The past isn't gone from the equations. It's right there, interacting with the present and future through the rules of quantum mechanics. Let me give you a concrete example. When an electron and a positron annihilate, they produce two photons. From one perspective, you have an electron and a positron coming together and turning into light. But from another perspective, using Feynman's time-reversed view, you have a single electron that emits a photon, reverses in time, emits another photon, and then continues forward in time. Both descriptions are valid. Both are different ways of looking at the same space-time events. And in the second description, the electron is literally traveling backward in time for a brief interval. The past and future are intertwined. The particle visits the past and then returns to the present. This isn't science fiction. This is how physicists actually calculate what happens in these interactions. And it works. The predictions match experiments to incredible precision. Now, here's something beautiful. Feynman didn't just accept these strange ideas, he used them. He turned them into tools. His diagrams, his path integral formulation, his whole approach to quantum mechanics was based on taking the idea of particles exploring all possible paths through space-time, including backward in time, and using that to make predictions. And those predictions are the most accurate in all of science. Quantum electrodynamics predicts the magnetic moment of the electron to 11 decimal places, and it matches experiments. That's not a coincidence. It's because the theory is capturing something true about reality. And part of that truth is that the past isn't gone. It's part of the structure that determines what happens. Now, you might be wondering, okay, fine, the past exists in some abstract sense. But so what? What does this mean for me? How does this change anything? And that's a fair question. On a practical level, it doesn't change much. You still can't go back and fix your mistakes. You still have to live with the consequences of your choices. You still age, grow, and eventually die. But on a deeper level, it changes everything. It changes how you think about your life, your identity, your place in the universe. If the past still exists, then every moment you've ever lived is still real. It's still part of the structure of space-time. Your childhood, your first love, your greatest triumphs, your worst failures, they're all still there, not just as memories, but as actual events, actual parts of the universe. You're not leaving them behind. You're carrying them with you in a sense, because you're a four-dimensional object stretched across time, and every moment is part of that object. Here's another way to think about it. You know how sometimes people say, "I wish I could go back to that moment"? Well, in a sense, you never left. That moment still exists. You're just not conscious of it right now because your consciousness is located at a different point in the four-dimensional structure. But the moment itself is still there, still real, still part of space-time. And in a strange way, that's comforting. Nothing is ever truly lost. Every experience, every person you've loved, every beautiful sunset you've seen, it's all still part of the universe. It exists eternally in the structure of space-time. Feynman had this profound respect for the universe as it actually is, not as we wish it were or imagine it to be. And when you look at the universe as it actually is, when you follow the mathematics and the experiments, you find that time is not what you thought. It's not a river carrying you from past to future. It's a dimension, like space, and all points in that dimension are equally real. The past exists, the future exists, and you're a thread woven through all of it, experiencing it moment by moment, but existing all at once in the greater structure. Now, let's talk about something else. Because there's a related idea that Feynman also thought about. If the past still exists, does that mean the future already exists too? And here's where things get tricky. In the block universe view, yes, the future is just as real as the past. It's already there, already part of the structure. But, and this is important, that doesn't mean you don't have free will. It doesn't mean your choices don't matter. Here's why. Even if the future is fixed, even if it's already determined, you don't know what it is. You still have to make choices. You still experience uncertainty. And your choices are part of what determines the future. They're part of the causal chain. So the future might be fixed, but it's fixed in part by the choices you make right now. It's not that the future is written and you're just reading the script. It's that the future is written and you're one of the authors. Think about it this way. In a book, every page exists simultaneously. The ending is already there from the moment the book is printed. But when you read the book, you experience it page by page. You don't know what's going to happen, and the characters in the book, if they were conscious, would experience themselves making choices, even though those choices are already determined by the text. The block universe is like that. All of time exists, but you experience it sequentially, and your experience includes making choices, feeling uncertainty, and living as if the future is open. And from your perspective, the future is open. You just happen to live in a universe where that perspective coexists with the deeper reality of all time existing at once. Feynman wouldn't want you to get too caught up in the philosophical implications, though. He was pragmatic. He cared about what you could calculate, what you could test, what you could predict. And the block universe view, the idea that past and future exist, it's useful because it gives you the right answers. It explains antimatter, it explains quantum interference, it explains why the laws of physics are time-symmetric, even though we experience time as asymmetric. It's a tool for understanding the universe, not a source of existential dread. But let me come back to the main point. The past isn't gone. It's still here, woven into the structure of space-time, encoded in the present, influencing everything that happens now. Every light ray from a distant star, every atom in your body, every memory in your brain, it's all a connection to the past. The past is not behind you. It's beneath you, around you, inside you. It's the foundation on which the present is built. And that's not just poetry. That's physics. Now here's something Feynman would absolutely insist on. Don't take my word for this. Don't take anyone's word for it. Look at the evidence. Look at the experiments. Look at the mathematics. Special relativity shows that simultaneity is relative, that there's no universal now. That's been tested. Time dilation is real. Clocks on airplanes run at different rates than clocks on the ground. That's been measured. Quantum mechanics predicts interference effects that only make sense if particles explore multiple paths through space-time, including backward in time. Those predictions have been confirmed in countless experiments. The cosmic microwave background radiation, the afterglow of the Big Bang, is light that's been traveling for 13.8 billion years. We can detect it. We can measure it. The past is not theoretical. It's observational. So when I say the past still exists, I'm not speculating. I'm describing the universe as physics reveals it to be. And Feynman, more than anyone, taught us to trust the equations, to trust the experiments, to let reality surprise us. He didn't cling to intuition when intuition was wrong. He followed the evidence wherever it led. And the evidence leads to a universe where time is a dimension, where all moments are equally real, where the past is not gone but preserved in the eternal structure of space-time. Here's the deepest part, and I want you to really sit with this. You are not a thing moving through time. You are a process. You are a pattern of matter and energy that persists and changes across time. The you of 10 years ago is not gone. That version of you still exists at its point in space-time. And the you of 10 years from now, that version already exists too, at its point in space-time. What you experience as the present moment is just your consciousness located at one particular slice of this four-dimensional structure. But the whole structure is you. All of it, from birth to death, that's the real you, the complete you, and every part of it is equally real. This is what Feynman understood. This is what physics tells us. And it's not sad, it's not diminishing, it's the opposite. It means every moment matters. Every experience is eternal. Every choice is part of the permanent structure of reality. You're not a fleeting spark in an indifferent universe. You're a thread in the fabric of space-time, woven into the cosmos itself, existing forever in the only way anything can exist, as part of the four-dimensional tapestry of everything that is, was, and will be. Now, let me be clear about something. I'm not saying you can visit the past. I'm not saying you can change it. I'm saying it exists. It's real. It's part of the universe. And that means something. It means the universe has memory. It means information is preserved. It means the story of everything that's ever happened is written into the structure of space-time and can never be erased. The past is not gone. It's just not accessible to you right now in the same way that distant places in space are not accessible to you right now. But they exist. They're real. They're part of the same universe. Feynman had this wonderful way of making you feel small and large at the same time. Small because the universe is vast and strange and operates according to rules that don't care about your intuitions. Large because you, tiny as you are, can understand those rules. You can do the math. You can run the experiments. You can figure out how reality actually works. And when you do, you find that reality is far more interesting than you imagined. Time is not a river. The past is not gone. The future is not empty. It's all one structure, one magnificent, interconnected whole. And you're part of it. So what's the takeaway? What should you do with this knowledge? Nothing, necessarily. You still live your life the same way. You still make choices, have experiences, move forward through time. But maybe, just maybe, you see it differently. Maybe you appreciate each moment a little more, knowing it's not fleeting, not disappearing, but becoming part of the eternal structure. Maybe you're a little less haunted by the past, knowing it's not gone, just located elsewhere in space-time. Maybe you're a little less anxious about the future, knowing it's already part of the structure, already woven into the fabric of reality. Or maybe you just think this is all crazy, and that's fine too. Feynman would be the first to tell you that physics is weird, that it doesn't match our intuitions, that it's okay to be confused or skeptical, but he'd also tell you to keep asking questions, keep looking at the evidence, keep following the logic wherever it leads, because that's how we figure things out. That's how we discover what's true. Here's the final thing I want you to understand. When we say the past isn't gone, we're not being mystical. We're not being poetic. We're being literal. The laws of physics, the mathematical descriptions of reality, they include all of time. Past, present, future. It's all there. It's all part of the solution to the equations. And those equations work. They predict things. They explain things. They've been tested to incredible precision. So when they tell us that the past still exists, we should listen. We should take it seriously. We should let it change how we think about time and memory and existence. The universe is not what you thought. Time is not what you thought. The past is not gone. And once you understand that, once you really grasp it, you can't unsee it. You see the universe for what it is, a four-dimensional structure where every moment is real, every event is eternal, and nothing is ever truly lost. That's what Feynman saw. That's what physics reveals. And that's the truth about time. So the next time someone tells you the past is gone, you can smile and think, no, it's not. It's still here. It's always been here. It's part of the structure of space-time, woven into the fabric of reality, existing eternally in the only way anything can exist. The past isn't gone. It's home. It's where we came from. It's what made us. And it's still out there, still real, still part of everything. That's not philosophy. That's physics. And Richard Feynman, genius that he was, understood it better than almost anyone. Now, let me tell you something else that Feynman would want you to know. This idea that the past still exists, it's not just about abstract physics. It has real implications for how we understand causality, how we understand the relationship between events. You see, we think of cause and effect as a one-way street. The past causes the present causes the future. It's a chain, each link connected to the next. And that's mostly true. But in the quantum world, in the world of particles and fields, causality is more subtle. Events can be correlated across time in ways that don't fit our simple cause and effect picture. Feynman worked on this extensively when he developed the theory of quantum electrodynamics with Julian Schwinger and Shinichiro Tomonaga. They showed that you could think of an interaction between particles as an exchange of virtual particles. An electron here creates a virtual photon. That photon travels across space and time, and another electron there absorbs it. And in the mathematics, that photon can travel forward or backward in time. It can connect events in ways that blur the distinction between cause and effect. The past influences the present, yes, but the present also helps define what the past was. They're locked together in a mutual dependency that's hard to visualize, but perfectly clear in the equations. Here's another thing. Feynman loved to point out that our psychological sense of time, our feeling that the past is different from the future, is tied to memory. We remember the past, we don't remember the future, and that's not mysterious once you understand entropy. Memory is a physical process. It requires creating records, storing information, and that process increases entropy. Your brain right now is in a higher entropy state than it was yesterday because it's accumulated more memories, more information about the world. That entropy increase gives you the sense that yesterday is past and tomorrow is future. But if you could somehow reverse entropy, if you could make your brain go to a lower entropy state, you'd remember the future instead of the past. Time would seem to flow the other way. The direction of time is tied to the direction of entropy increase. And entropy increase is statistical, not fundamental. What this means is that the arrow of time, the thing that makes the past feel different from the future, it's emergent. It arises from the collective behavior of many particles, not from the laws governing individual particles. And that's why the past still exists, because at the fundamental level, the level where the laws of physics operate, there is no past and future. There's just space-time, and all parts of it are equally valid. The asymmetry we experience, the feeling that time has a direction, that's about us, about how we interact with the world, not about time itself. Feynman had this incredible lecture where he talked about the reversibility of physical laws. He pointed out that if you filmed almost any microscopic process and played it backward, you couldn't tell it was reversed. An atom emitting light looks the same as an atom absorbing light if you reverse time. A particle collision works the same forward and backward. The laws don't distinguish. And he'd ask, so where does the irreversibility come from? Where does the arrow of time come from? And the answer is always the same. From the initial conditions, from the fact that the universe started in a low entropy state at the Big Bang and has been increasing in entropy ever since. That's it. That's the only thing that breaks the time symmetry. And it's not a law. It's a boundary condition, a fact about how the universe began. Now think about what this implies. If the arrow of time comes from entropy, and entropy is about statistics and probabilities, then the arrow of time is not a feature of space-time itself. Space-time doesn't have an arrow, it's symmetric. All moments are on equal footing. The arrow is something we impose, something that emerges from our perspective as entropy-increasing beings living in a universe that started with low entropy. But the underlying reality, the space-time structure itself, treats past and future identically. They're both real. They're both part of the fabric. Here's something else Feynman understood deeply: the relationship between quantum mechanics and time. In quantum mechanics, particles exist in superposition until measured. They're in multiple states at once. And when you measure them, the superposition collapses and you get one definite outcome. But here's the weird part. That collapse seems to violate time symmetry. The forward evolution of a quantum system is reversible. You can run it backward. But collapse is not reversible. It picks one outcome and discards the others. So what's going on? Is time symmetry broken by quantum measurement? Feynman wrestled with this, and his answer essentially was that collapse is not a fundamental process. It's an effective description of what happens when a quantum system interacts with a macroscopic environment. The environment acts like a measuring device, and the interaction creates correlations that make the system look like it's in one definite state. But fundamentally, the whole system, quantum particle plus environment, is still evolving according to time-symmetric laws. The appearance of collapse, the appearance of irreversibility, it's about our limited perspective, our inability to track all the degrees of freedom in the environment. It's not about time itself. This ties back to the block universe view. If all of time exists, if past and future are both real, then quantum mechanics is describing correlations across time. When we say a particle is in a superposition, we're saying it's correlated with future measurements in a specific way. And when we measure it, we're not changing the past. We're discovering which branch of the wave function corresponds to our location in space-time. The past and present are consistent because they're part of the same structure. The wave function describes the whole structure, all of time, and measurements reveal which part of that structure we're in. Okay, now let me tell you about something really profound that Feynman said. He once remarked that the same electron could be moving backward and forward in time, multiple times, creating what looks like many electrons. This was a half-serious idea he discussed with his advisor John Wheeler. Wheeler suggested that maybe there's only one electron in the universe, and it just zigzags back and forth through time, creating the illusion of many electrons. Every electron you see is the same electron at different points in its journey through space-time. And every positron, every anti-electron, is that same electron moving backward through time. It's a crazy idea, and Feynman knew there were problems with it. The number of electrons and positrons doesn't match, for one thing, but the idea captures something deep. It captures the idea that time is not what we think, that particles can move through time in ways that defy our intuition, and that the past and future are so intertwined that even identity, the question of whether two electrons are the same or different, becomes ambiguous. This is the level of strangeness we're dealing with. And Feynman embraced it. He didn't shy away from the weirdness, he used it. He turned it into a tool for understanding reality. And what he found is that when you take these strange ideas seriously, when you follow them to their logical conclusions, you get theories that work. You get predictions that match experiments. You get a deeper understanding of how the universe actually operates. The past isn't gone. Particles can move backward in time. Space-time is a four-dimensional structure where all moments exist. These aren't philosophical speculations. They're features of our best theories of physics. And those theories are tested every day in laboratories around the world. Let me give you one more example of how the past persists. Quantum entanglement. When two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance and thought it proved quantum mechanics was incomplete. But experiments have confirmed it's real. Now, here's the thing. Entanglement creates correlations across space, but it also creates correlations across time. You can have particles that are entangled not just with each other in space, but with their own future and past states. Your measurement now can be correlated with a measurement that happened in the past or will happen in the future. The past state of the particle is not independent of the present state. They're connected, entangled, part of the same quantum system. And that system spans time, not just space. Feynman's path integral formulation makes this explicit. When you calculate the probability of a particle going from point A to point B, you sum over all possible paths, and those paths include loops in time. A particle can go forward, then backward, then forward again, and all of those paths contribute to the final answer. The past is not a separate thing. It's part of the same calculation. It's woven into the quantum description of reality. The particle's history is not a sequence of definite events. It's a superposition of all possible histories, and those histories include ones that visit the past multiple times. Now, I know this sounds like science fiction. It sounds too strange to be true. But here's the thing. These ideas have consequences. They make predictions, and those predictions have been tested. The interference patterns you see in quantum experiments, the precise values of physical constants, the behavior of particles in accelerators, all of it matches what you'd expect if particles really do explore all possible paths through space-time, including backward in time. The math works, the experiments agree, and the simplest way to understand why is to accept that the past still exists, that it's part of the structure particles are exploring. Feynman would tell you not to trust intuition here. Intuition is built from experience, and our experience is limited. We don't experience quantum superposition directly. We don't experience time reversal directly. We don't experience the four-dimensional structure of space-time directly. So of course it feels weird when physics tells us about these things. But that doesn't make them any less real. It just means reality is bigger and stranger than the small corner of it we evolved to navigate. And the way to understand reality is not to force it into our intuitive categories, but to let the evidence guide us, to follow the mathematics, to accept that the universe might work in ways we didn't expect. Here's the beautiful part. Despite all this strangeness, despite the weirdness of particles moving backward in time, and the past still existing, and the block universe and all of it, the theory works. It's not just philosophically interesting. It's practically useful. Engineers use quantum mechanics to design transistors and lasers and MRI machines. Physicists use it to understand stars and black holes and the Big Bang. The Global Positioning System, GPS, requires corrections for both special and general relativity to work accurately. If we didn't understand how time dilation works, if we didn't know that time passes at different rates in different places, GPS would be off by miles within hours. This stuff is real, it's been tested, it works, and it tells us the past is not gone. So here's where we are. The universe is a four-dimensional structure called space-time. Every event, every moment, is a point in that structure. The past is not behind us in some metaphorical sense. It's at different coordinates in space-time, just as real as the present, just not accessible to us because we move through time in one direction due to entropy. Our memories are physical records of past events, but the events themselves still exist in space-time. Light from distant stars is literally the past reaching us in the present. Every atom in your body carries information about its past, and the laws of physics describe all of time, past, present, and future as parts of a single unified whole. That's what Richard Feynman understood. That's what physics tells us, and that's the truth about time.